Hey everyone, we're going to take a look at number 22 in section 4.3. This problem asks us to find the critical points for this function. There's a lot of parenthetical comments, information that you need to know to solve the problem, so make sure that you clearly read those things to know how to answer the question correctly. Your function for this problem should be very similar to this. These numbers 4 here and the 6 up here, exponent may be slightly different. First thing to note about this function is the domain. The domain of this function is all real numbers, right? The domain of all exponential functions like e to the x is all real numbers, times a polynomial function, which also has a domain of all real numbers. And that's important because when you're finding critical points, remember those are points that are in the domain of the function for which the derivative is 0 or undefined. And so we do need to of course, find the derivative first off in order to find our critical points. And because I have a function that is the product of two functions of x, right? Think of this as being the first function 4x to the sixth. The second function is e to the x. I'm going to use the product rule. So the product rule says take the derivative of your first function 4x to the sixth. So that's what the prime mark means, times the first function plus 4x to the sixth times the derivative of the second function. And so this one's easy. I hope everyone knows the derivative of e to the x is just e to the x. And then by the power rule, the derivative of 4x to the sixth is 24x to the fifth, right? Bring the 6 down. 6 times 4 is 24. Subtract 1 from the exponent. And that's what we get. So here's our derivative. Now, to be helpful, I want to know when the derivative is 0 or undefined. Clearly, it's never undefined. The domain of the derivative is all real numbers, just like the original function, of course. To help me find when the derivative is 0, I'm going to factor this expression. And notice I can factor out the greatest common factor of what? 4 and 24. I can pull out a 4. X to the fifth, x to the sixth. I can pull out a x to the fifth. And I can factor out a e to the x, which is a common factor to both terms. So when I bring out, factor out rather the 4x to the fifth e to the x, what's that leave me? Well, just 6 here, right? 6 times 4 is 24. Everything else is there. Here, when I factor out 4x to the fifth e to the x, I'm just left with 1x, as everyone hopefully sees that. So here's how it factors. And then clearly I can see now the derivative is going to be 0 either when x is 0, right? Because, x to the fifth will be 0 when x is 0. Or when what? X is -6, because everything in the parentheses here in that case would be 0. Of course, e to any power is always greater than 0 and is never equal to 0. So the only two values of x that make the derivative 0 are these. They are in, of course, the domain of the function, which is all real numbers. So these are our critical points. And so make sure you clearly know how to list those. I think the prompt is x equal and then a box. So you're just putting the numbers separated by a comma. It doesn't matter the order that they're in. So again, be sure you read those comments about how to enter the information. Now, the other thing is that we need to find out where this function is increasing and decreasing and where we have local extrema. And so we're going to do a sign check of our derivative, and then we're going to use the first derivative test to determine the location of any local extrema, local maxima or local minima. So the way I do the sign check again, as I've done in the lectures, I'm just going to draw a real number line denoting all real numbers. And in particular, I want to put the two numbers in the correct order where we have critical points, the two critical numbers, if you will, -6 and 0. So of course the derivative at -6 is 0, and at 0 it is also 0. Now all we need to do is check the derivative for any value less than -6, like say -7. And if I plug -7 into my derivative, I'm going to plug it into this factored form here. First of all, note e to the -7 is not a negative number. E to the -7 is a positive number, right? It's 1 divided by e to the 7th power. The range of e to the x is everything greater than 0. So this term will always be greater than 0 no matter the value of x. But over here I'll have -7, right, to the 5th power. Well, negative number right, raised to an odd power is going to be negative, right? The result will be negative because what does it mean? You're multiplying -7 times itself 5 times. If you have an odd number of negatives in any product, the product is negative. So that would make this whole thing negative. But then notice here, 6 plus -7, that's -1. So I'm multiplying a -1 times some negative number, which is positive. Okay. Again, you can enter this into your calculator and you can plug in x equal -7 and see the actual value. The important thing is that it's positive. In fact, that's true for any number that any value of x you plug into the derivative that's less than -6. So between -6 and 0, maybe I picked -1, right? -1 is in that interval. Here, -1 to the 5th power will be -1. E to the -1 is a positive number, 1 divided by e. And then 6 plus a -1 is 5. So this will be negative, this will be positive. A negative times a positive is negative. So everything, every value of x between -6 and 0 makes the derivative negative. And then something greater than 0 like 1. So this will just be 4. 1 to the 5th is 1. E to the 1st is e. So this is just 4e. 6 plus 1 is 7. 7 times 4, I get 28 times E. Bottom line is that's a positive number. Okay. So with this information, we can now answer the questions. Where do we have local minima? By the first derivative test, that has to happen where the derivative changes what? From negative to positive, because when the derivative is negative, the function is decreasing. When the derivative is positive, the function is increasing. So we're going down and then up, and so we must have a local minimum at x equals 0. So local minima at x equals 0, that's one of the answers for this particular problem. And then local maxima is going to be at x equal -6. Why is that? Because by the first derivative test, we have a sign change in the derivative from positive to negative as we go from left to right, which means the function is changing from increasing to decreasing at -6. So we have a local maxima there. As I've already said, the function f is increasing on the intervals where the derivative is positive. So that's everything less than -6. Notice the way they want you to do that with interval notation. So parentheses, all right, -infinity, comma, -6. That's everything less than -6. And then this union symbol means or. When you're doing multiple disjoint intervals, you need to connect them with that. And that's the way they want you to write the answer. So again, the derivative is positive for values greater than 0, so that's written in interval notation this way. And then f is decreasing where the derivative is negative. That's between -6 and 0, which is written that way. Okay, so hopefully this is helpful for this problem. If not, let me know.